All right, hello everyone. Today we're going to start our organic naming series, and we're going to be naming alkanes and halogenoalkanes. So alkanes, you guys might remember from sophomore year, are compounds that are composed of just carbon and hydrogen. They have only carbon-carbon single bonds. They can be referred to as hydrocarbons because they contain only carbon and hydrogen. And you also might remember that they have a general formula, which is CN H2N plus 2. So to find the number of hydrogens that go with the number of carbons, you just multiply the number of carbons by 2 and add 2. They are named using prefixes that we also learned sophomore year. And so those prefixes to review are, the prefix for 1 is meth, for 2 it is eth, for 3 it is prop, for 4 it is bute. Right? And then after 4, we start using the same standard prefixes that we use with our binary molecular compounds like carbon dioxide. So for 5, it is pent. For 6, it is hex. 7, hept. 8, oct. 9, known. 10 is dec. And then for 11 and 12, in case you're curious, 11 is undec, 110. And 12 is dec. Now, we'll never actually have to use those on the exam. On the exam, we only go up to 6 carbons for our longest chain, but it makes it more fun if we know more of them. Now, the kind of alkanes we talked about initially would have been considered straight chain or normal alkanes. That means that all the carbons would just be connected in a row and there'd be no branching at all. So that would be easy to name. The compound with 5 carbons connected in a row would just be pentane. But alkanes have the ability to get a lot more complicated, right? You can get little offshoots, little branches to the chain. Those branches are called substituents. And they're composed of just carbon and hydrogen also, so they're kind of like alkanes, but they're, little offshoots. And so we call them instead little subset groups, alkyl groups. And those are named just based on the number of carbons as well, but with the -ol ending. So when you have just a 1 carbon offshoot, right, that would be CH3, that is called a methyl, METH, methyl group. So 1 carbon, the meth, and then the -ol, YL, to indicate it's not the parent chain, the longest chain, but instead it's a substituent. So 2 would be an ethyl group. 3 would be a propyl group. And then you can have the option of connecting a propyl at the very end carbon, then it's just a propyl group. But if it's connected at the middle carbon, then we call it isopropyl. So when you look at a more complicated alkane that has some branching in it, you can identify little substituent groups in there. So right here, 3 carbons, so that is a propyl. And then, oh, sorry, just joking, it's an isopropyl. And then down here, right, if we pretended, which isn't technically correct, that this middle chain was the longest chain, then this would just be a plain propyl. Okay, and then over here we have that same structure, just kind of filled in with the missing hydrogens, the hydrogens that are missing. Okay, so what about naming a branched chain alkane that has these little offshoots? Well, let's use this as our example. So the first thing we're going to do is we are going to identify the longest chain in the structure. So a lot of times it goes straight through the middle, but not always, so you have to be careful about that. So this is a carbon chain that is 1, 2, 3, 4, 5, 6, 7, 8 carbons long. And so this is, as its parent, going to be a version of octane. And then the little offshoots that we see, right, they're going to be listed before the name octane as the substituents. Now, before we list those substituents, we have to number the chain. So we want to number the chain so that the first offshoot, the first substituent, gets the lowest number. So in the case of our example, we're going to number the carbon on the left, carbon 1, 2, 3, 4, 5, 6, 7, and 8. If the first substituent had been closer to the right-hand end, then we would have numbered from right to left instead. So we'll see an example of that later on. But in this case, the first substituent is closest to the left, so we number from the left. If it's a tie, by the way, right, if you have a substituent, one carbon in on both ends, then you break the tie by looking at the next substituent. If there's a second substituent, then you number it so the second substituent gets the lowest number. And if it's still a tie, then it's based on alphabetic order, but that doesn't come up very often. Okay, after we number our carbon chain, then what we're going to do is identify our substituents and the carbon that they are attached to. Each carbon is either a part of the parent chain or it's a part of the substituent. It's not part of both. So in our example, this carbon, that's one carbon, that's a methyl, and it's at carbon 2. We have another methyl, and that's at carbon 6, and we have an ethyl at carbon 5. So we're going to include all that information kind of as a little prefix before we write the name octane, the name of the parent. Okay, so each substituent needs not only its name, but its location, right? If there are two of the same substituent, like we have here, the two methyls, we're also going to include the prefix di for 2. And then when we list these, the way we'll decide what to list first is just alphabetically. So alphabetically, ethyl comes before methyl, so I'll write it first. First thing I'm going to write is the location of that ethyl. So it's on carbon 5. I write 5-ethyl. Then another dash. And now I have my two methyls. One is at carbon 2. One is at carbon 6. So I do 2, 6 dash dimethyl. And then my parent comes in. It's 8 carbons long, and it's an alkane, so it gets the suffix ane. And so that compound is 5-ethyl 2,6-dimethyl octane. Now when you're writing the numbers and letters, right, whenever you have a number and a letter coming up, you use a dash. You don't use dashes between letters ever. So the dimethyl octane is all one word. And then if you have your numbers like 2 and 6, you separate those with commas. So let's try a couple more of these. Okay, now our first example here on the left, this is a little tricky because the longest chain is not through the middle. If I count through the middle, I have 1, 2, 3, 4, 5, 6, 7 carbons, but I get a slightly longer chain if I go and make a little turn. 1, 2, 3, 4, 5, 6, 7, 8, 9. So my longest chain takes a little bend, a little jog. Okay. Now, what end am I going to number from? Well, if I number from the left, the first substituent, this little methyl here, is going to be on the 3rd carbon. If I numbered from the right, my first branch 1, 2, 3, 4, 5 wouldn't be until carbon 5. And so once again, I'm going to number from the left. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then I can go ahead and identify my substituents. Now this is a methyl. And then you're looking at this and you're thinking, hey, this is kind of weird. What is it? But if you look really closely, it's a 3-carbon chain, and it's connected in the middle. So 3 carbons make it a propyl, and connecting in the middle makes it an isopropyl. So isopropyl, iso is the only prefix that we're going to be alphabetizing. If we have like a di or a tri, we ignore those, but not the iso. So to list this, isopropyl comes first alphabetically. So I write 5-isopropyl. And then my next substituent, 3-methyl. And then we're 9 carbons long, so that's the known, and it's an alkane, so that's the known name. Next one, longest chain. Well, there's a couple of ways you can do the longest chain, but in this case, it doesn't really matter. It can be either through the middle, right? And that's 1, 2, 3, 4, 5, 6 carbons, or it can be 1, 2, 3, 4, 5, 6 carbons. It doesn't matter how you identify it. It's still going to be the same name. So I'm going to go through the middle because it makes it a little bit easier to number. Okay, so numbering this time, I'm going to number from the right, 1, 2, 3, 4, 5, 6, because that gives my substituents on carbon 3. If I numbered from the left, they would be on carbon 4. And then both of those are ethyls, and so my name is going to be 3, 3. They're both on carbon 3, so I write 3 twice. I know, a little redundant. Diethyl, and then we're 6 carbons long, hexane. There you go. All right. Now, what about working in the opposite direction, going from a formula to a name? Well, the other way, going from a name to a formula. Well, in this case, we're just kind of working backwards. We're starting with our parent and drawing our skeleton here. So that is 1, 2, let me move this over so I have enough room for that other one over there. So I have 6 carbons, 1, 2, 3, 4, 5, the other one here, 6, right? And then I get to choose, do I want to count from the left or from the right? Well, I'm going to count from the left. Then I can just start putting on my substituents. So 3-ethyl, counting 1, 2, 3 carbons. An ethyl is 2 carbons. And by the way, it doesn't matter if I put it above or below. Same thing. And then at carbon 2, I need a methyl. So there's my, my methyl. And then the final thing I need to do is I need to fill in my hydrogens. So remember that carbon always makes 4 bonds in these organic structures. So I just look at how many bonds each carbon is making, and I fill in whatever number of hydrogens I need. So in this case, the first carbon's only making 1 bond. I need 3 hydrogens in there. Going down the middle, second carbon is making 3 bonds, so it gets 1 hydrogen. The third, same deal, 1 hydrogen, and then the next 2 each need 2 hydrogens, and then on the end it's CH3. And I also have to fill in the hydrogens on my substituents. So this carbon is making 2 bonds, so it needs a CH2 and then CH3, and my methyl is CH3. All right, okay, this last one, oh gosh, why did I do this to myself? There are 10 carbons in my parent. So 1, 2, 3, 4, 5, 10. Okay, then I'm going to count from the left again. 6 in, 1, 2, 3, 4, 5, 6. Put in an isopropyl. So that's 3 carbons connected in the middle. And then I have a 3,3,7 trimethyl. So on carbon 3, 2 methyls. And then on carbon 7, 1 methyl. And again, it doesn't matter whether I draw those carbons above or below the chain. It's equivalent. And then I can go ahead and fill in whatever carbons or sorry, whatever hydrogens I need. Already making 4, CH2, CH2, CH, CH, CH2, CH2, CH3, and then across the top, that's a 3, a 1, and a 3. Just checking and seeing however many carbons need to be made. Okay, so that's how you name alkanes. And then very closely related to this are halogenoalkanes. The only difference between an alkane and a halogenoalkane is the substituents on a halogenoalkane contain a halogen, right? So some halide functional group, fluorine, chlorine, bromine, or iodine. Naming is very similar to regular alkanes. We just use the prefixes of fluoro, chloro, bromo, and iodo, and we place those in alphabetically just like we would if it were an alkyl group. So let's do a couple of examples here so you can see how this works. So on the first example here, there's chlorine on CH3Cl. So that's just one. In this case, we don't need a number. It's just going to be chloromethane. Okay, and then there are 2 chlorines. This will be dichloromethane. And then CH3Cl3 is, or CHCl3 is trichloromethane. Now we have some ethanes with bromine as the substituent, so bromide, a bromo group. So in this case, it doesn't need a number because wherever the bromine is, there's only one of them. It's always going to be carbon 1. So this is just bromoethane. Okay, but in our next 2 examples, we have bromine on the 2 adjacent carbons in the first and the bromine on the same carbon in the second. And so we do have to identify carbon numbers to differentiate between those. So our middle example here would be 1, 2 dash dibromoethane. And our third example would be 1, 2 dash di. Oops, sorry, just joking. Erase 1, 1. So that's 1, 1 dibromoethane. A couple more examples. Okay, so this one, 1, 2, 3, doesn't matter which side I number from, it's equivalent. And this is 2 dash fluoropropane. Okay. Next example. Now we have substituents on both ends. I'm going to count the leftmost carbon as carbon number 1 because that puts this iodine on carbon 1, gives it the lowest number. 1, 2, 3, 4. Okay, and then we have an iodo group and a methyl group. We list these alphabetically. So that is 1 dash iodo, 3 dash methyl butane. Okay, next one. What's our longest chain? Oh, a little bit tricky here because it's not through the middle. 1, 2, 3, 4, 5, 6 carbons. If we instead do the little turn, 1, 2, 3, 4, 5, 6, 7 carbons, that gives us our longest chain. So here it is. Okay, and where are we going to number from? Well, we're going to number from the right because that will put the first chloro at carbon 2. 1, 2, 3, 4, 5, 6, 7. Okay, so our substituents are chloro and ethyl. So this will be 2, 3 dichloro dash 4 dash ethyl heptane. Okay, right, and then our very last example, this is like kind of the most rudimentary structure you can have. You see these lines to represent organic structures sometimes. Remember when we were talking about benzene? You saw it then. So when you see a structure like this, and this wouldn't show up on the exam, but you'll see it at some point in the future, right? What you're understanding is that at an end of a stick, you're understanding that there's a carbon, and at every angle, you're understanding that there's a carbon. Okay, so we have all those carbons, carbon there. This has a bromine at the end, so there's no carbon there, but there are carbons there. Right, and then you proceed to name it just like you always would. And in this case, you can name through the middle. That gets you longest chain. The same length if you turn the corner, so it doesn't matter which one you do. Okay, and numbering here, we're going to number from the right. 1, 2, 3, 4, 5. That gives those two substituents the lowest numbers. And again, we go alphabetically. So we have a bromine at carbon 2, so 2-bromo. Next alphabetically comes ethyl, and that's at 3-ethyl. And then we have methyl up there above carbon 2, 2-methyl. And this is 5 carbons, so that is pentane. And there you have it, naming alkanes and halogenoalkanes. Talk to you later.